last session, we finished up most of the textbook, and then we started a new chapter, which is not in the textbook, and it's about machine learning in general. But what have we done so far? I'm going to do a quick recap of what we covered last session, and then I'm going to continue with the rest. So far we learned how to import data. So somebody gives us one file, two files, or multiple files. Perhaps they are in the form of a CSV file or multiple CSV files. Then we learned how to import the data in R, and the command that we were using was read underscore CSV. But we know that CSV files are in the form of text, and we had to convert them into integer or double or date for us to be able to work with them. And that's why doing parsing was very important. And that's where we learned about strings and regular expressions to be able to work with CSV files and be able to properly parse them. Then it was a matter of tidying our data. Our data should be in the form that in each row, we need to have an observation. In each column, we need to have a variable, and two commands that were really helpful for us to make our data tidy was pivot longer and pivot wider. The other thing that we learned, because we might have multiple data sets, we needed to learn how to join them together and merge the data sets together. And a major command here was left join. Then we learned how to transfer our data. And the aim here is to understand the data. So we are doing exploratory data analysis. So we have to transfer the data. And the commands that we had was filter the data, basically select a subset of your observations, or select, which is you're going to select a bunch of columns, or sorting and arranging your data and rearranging the observations. Then a major part of data science is visualization. And a major package in R is ggplot. It's very useful. It's much better than what you're going to do in Python later on. But ggplot is very nice, and it helped us visualize categorical and continuous variables, actually their distribution. It also helped us visualize categorical versus continuous, basically pairs of variables, or continuous, categorical. And this was giving us more idea for us to be able to explore the data. Then we started doing modeling. And the major aim for modeling in this course was to understand the data. It wasn't to come up with new models, but to actually use them in practice on our data and make judgment. For instance, if you do a linear regression, then you would look at your residual, and this way you're taking out the effect of one variable from your data and then looking at the other variables that are left. And then we learned how to do multiple models. And throughout the semester, you have been communicating your results with me and Kayvon. You were writing reports and you were submitting your work through GitHub. And these are actually what you're going to use when you find a job or go to grad school later on. And the major component was programming. We learned about for loops, we learned about while loops, we learned about classes, we learned about functions, and we learned about maps, which is a nicer way of writing for loops in R. Now we are going to continue with models. So the only model that the textbook is going over is the linear model, and basically doing linear regression. Now we want to change our task a little bit. What if our task is different? What if our task is in the form of classification? What is an example of classification? Somebody gives us a data set, then we have to divide the data into training, validation, and testing. And let's say your task is the data is in the form of emails. So you want to know when an email arrives at your inbox, should it go into your inbox or should it go into your spam folder? So let's say class A is the good class, the ones that you want to read, and class B is the class that you don't want to read. You want these emails to end up in your spam folder. So what is the x-axis and y-axis here? For that particular example, the x-axis could be, for instance, the count of the number of X word, for instance, price, that is appearing in your email. The y-axis could be the count of the number of words that are Y words, for instance, I don't know, hello or dear sir. So words like that, or it could be even pairs of words. So that's your X coordinate, that's your Y coordinate. These are all of the emails that you already classified as a spam. You just mark them as a spam. So these are bad and these are good. So let's say you have two classes. And we are approaching this problem from the perspective of machine learning. In machine learning, you want to end up with a software that you're gonna put into production. For instance, you have a company, maybe you are Google, and then you have a service that's your Gmail, and you want to provide some service to your customers. An email comes in for your customer, it's a question mark. We don't know what class it belongs to. And then we want to classify it either as a spam or not spam. So a simple algorithm to do that, the simplest one, is the k nearest neighbor. You look at the k nearest neighbors of this question mark, you have two spams, one not a spam, and then you vote. It's gonna be a vote of 2 versus 1. So you're gonna mark this question mark as a class B. A key parameter, these types of parameters that are defining your method in machine learning, they are called hyperparameters. And the way that you're gonna adjust them is you're gonna take a look at, for instance, some metric. We are gonna go over what metric is good for classification. You're gonna look at some metric, let's say it's about accuracy, and then you compare all of these models on your validation data. So you divide your data set into training, validation, and testing. Training is used for training. Validation is used for coming up with the best hyperparameters, 3 versus 7. And testing is when you want to test your algorithm in production. You first test it and then you put it into production. So you're not allowed to train neither your parameters nor your hyperparameters on your test data. So you're not allowed to touch your test data. It's the last step that you do. So is everything clear so far? Okay, perfect. So now let's go ahead and download some data and try to work with it. And the idea here in this lecture and in the rest of the lectures in this course is to just introduce to you at a very superficial level what these algorithms are. But then when you go to your more advanced courses, you're gonna see more of the details of each algorithm. For now, we want to be able to use them in R and analyze our data. For us, we are gonna use it as exploratory data analysis. We just learn the command and use it and make judgments about that data. So let's say this is our data. And there is a famous scientist who actually collected this data. It's about, you have a bunch of flowers. There are three major categories: versicolor, setosa, and virginica. These are your three classes of flowers. And then your features are gonna be what is your sepal width and what is your sepal length, what is your petal length and petal width. So you're gonna have 4 features. So these are your variables. You have 4 variables, and then the last one is the one that you want to predict. So a scientist was labeling this data, and for you to be able to label this data, you needed to be a scientist. But now we want to replace the scientist with a machine learning technique. If a new flower comes in, we don't want to call the scientist again. He already worked for us. He or she already worked for us a lot. We want to call a machine learning algorithm and just classify it. So that's the objective. Let's download the data. The data is already in R. It's actually in library tidyverse. So that's the data. We are first turning it into a table. We know what a table is by now. Then we look at the head of our data frame, and then we count the number of observations and the number of variables, and we are using the dim command. So there are a total of 150 observations in this data. The number of variables is 5. 4 of them we are going to use for prediction, and the last one we are going to use for training. In total, you have 5 variables. And let's take a look at the summary of the data. So this is really important because once you look at this summary, you're gonna see that the mean of the first column is around 5. The mean of the second column is around 3. Same thing here. But then the variation and the scale of these parameters, these variables, is very diverse. So the minimum value for this variable is from 0.1 up until 2.5. That's the maximum. From 1 to 6, 2 to 4, and 4 to 7. And we also have 3 classes, and we have 50 observations per each class. So the data is balanced. But that's a problem when you have the mean being non-zero and the minimum and maximum being so diverse among your data. That's a problem when it comes to machine learning. because it's going to have a training step, and the training step is usually some maximization or minimization, which has to converge. If these variables don't have the same scale, your algorithm is going to have trouble converging. So we have to normalize the data. But before you normalize the data, this is a mistake that many people in machine learning make. They first normalize the data and then divide it into training and testing. That's a mistake because you're leaking some knowledge about your test data. Remember, you're not allowed to touch your test data, but now you're taking the mean of the test data, and that's going to be helpful for your training algorithm. So it's sort of cheating. So we should never do that. First, we are going to split the data into training and testing and validation. For this topic, I'm not using validation because I'm not interested in what is the best K, but the proper way to do it is to have uh, perhaps around 60% of your data being training, 20% being validation, and 10% being testing. But for now, I'm just going to use train and test data. And then the way you're doing it is you sample a fraction, 70% of your observations. You put it in your train data frame. Then the rest of them, this is where we are going to use the commands that we learned before about when you have two different data frame, how do you work with them? Now we need the anti-join. This is all of the observations that are not in the training. They are going to end up in your testing. Okay? Now this is the time to normalize the data. We are going to compute the mean and the standard deviation from only the training data. So you first split your data into training and testing, and then you compute the mean. This is where we learned about, we are going to use the function that we learned about, map. This is a for loop, but it's doing it in a very nice way in a one-liner. So rather than writing a for loop, you're just going to call the map function. So now that we compute the mean and the standard deviation of the data, we are going to normalize our data. What we do is take the data, the first four columns, and we know that the first four columns correspond to sepal length, sepal width, petal length, petal width. And what we are going to do is subtract the mean and divide by the standard deviation. You do the same thing for your test data. You divide by the mean and the standard deviation. But this mean and the standard deviation are coming from your training data. So we are not cheating. The mean and the standard deviation are coming from the training. Okay, let's do it. Now that we did that, let's take a look at the head of the training data and the number of observations and a summary. So that's our data. Clearly the scale has changed. It's around 0. Some of them are positive, some of them are negative. The number of observations that you have in your training data is 105. So we are not using the entire data set. We are just using 70% of it. The number of variables is the same as before. Now look at the scale. The minimum and the maximum, they are all around -2 to 2, all of these values. Not only that, the mean of your data is 0 for all of your columns. And then your training data has 38 observations for setosa, 31 for versicolor, etc. What happened to our test data after this transformation? They have nice values also, but then if you look at the mean is not 0. It means that we are not cheating. So the mean is non-zero on your test data. But what is our objective in the end? We want to classify. Now our data is pre-processed, and almost 70% and more of a data scientist's time is gonna be spent on cleaning the data, putting in the right format, in the correct format. And that's usually the most boring part. And the interesting part is gonna be around 20% or 30% of your time. Now we are going to the interesting part. What library are we gonna use to do k-nearest neighbor? So this library you have to install, and we are now departing from tidyverse. This is another package that we are installing, and I have already installed it, but probably you guys are gonna install it later on after the class today. Now it's time to feed the k-nearest neighbor algorithm and use it properly. So whenever you end up with a new function, you just call the help on it, and then it's gonna tell you how to use it. We're gonna do k-nearest neighbor. We have our training data. We have our test data as the second argument, the classes, and then what k we are gonna use. What is our k nearest neighbors? And the rest of them are probably not important for what I'm trying to do now. And then you can also take a look at some of the examples. Okay, now we know how to use it. So the first argument is gonna be the first 4 columns of our data. The second one is the test data, the first 4 columns. Our data are already normalized and clean. Then you need to feed it the classes, and these are gonna be the species column. And we have 3 classes and how many neighbors to look around. So let's go up there and see what we just did to the figure here. Rather than 2 classes, we have 3 classes, and the classes are these 3 types of flowers. Then we are gonna look at 10 of our nearest neighbors and then vote for a new data point for our test data. We are gonna look at our training data, the 10 nearest ones, and then use the training data to vote. If there are more versicolor around this new flower, we are going to label that as a versicolor. So, and that's exactly what this algorithm is going to do. So it doesn't matter how to implement it, because this is going to be the topic of your more advanced classes. For now, we want to learn how to use it. Okay, we did our predictions, and we are doing it on our test data. If you look at PR, it made some predictions, but how are you going to trust the algorithm? What's your metric? So a good way to do this is to look at your ground truth. This is where the ground truth for test data comes in, because we know for each observation in our test data what is the correct label. And then you're going to call the table command, and that the table command is going to compare PR, the predictions of the model, and all of the species, the ground truth, on the test data. So this is our test data. And then let's take a look at it. Our algorithm, k nearest neighbor, is predicting 12 setosa as a setosa. So 12 of them are being classified correctly. 0 of the setosas are being classified as a versicolor. 0 of the setosas are being classified as virginica. So it's making no mistake when it comes to setosa. So our algorithm is not confused between setosa and other classes. With versicolor, we are making one error. The diagonal ones are the correct ones. Setosa is being classified as setosa, versicolor being classified as versicolor, virginica being classified as virginica. And you have 13 observations, 18 observations, and 12 observations that are correctly classified from your test data. And then there is versicolor being confused. There is only one of them being confused with virginica. So one observation is wrong there, and a virginica is being confused as a versicolor. So that's how you read a confusion matrix. So this is called a confusion matrix. But let's say you want to come up with the best K. The K that we used was 10. What happens if it is 13? What happens if you use 7? So there is a huge flexibility that you have in the choice of K. But then if you look at the confusion matrix, it's not a single metric to help you decide between these two choices. So what we are going to do is turn the confusion matrix into a single number that we can use to compare two models. And that's called accuracy. That's a metric that we're going to use. And that's basically the sum of the diagonal of your confusion matrix. So this is the number of predictions that were correct out of your test data. And then the sum of the entire. So you have two sums here. One is doing a row sum, and then the other one is doing a sum on the entire matrix. So in the end, you're gonna get 12 plus 18 plus 13 divided by 12 plus 18 plus 13 plus 2. And that's how accurate your model is. It's 95.55% accurate. This is the accuracy metric. So now let's go ahead and play around with K a little bit. If K is 1, we are gonna make more mistakes, and then the accuracy drops. So it means that K being 10 was better than K being 1. But actually, there is some uncertainty here. So you have to do this exercise multiple times for you to be as sure as possible. If K is 2, these are our predictions. That's the confusion matrix. So we made more mistake, and it's now 88% accurate. If K is 3, so far our best model was K being 10. But this exercise that I'm doing, you have to do it on a validation data, not on your test data. So this one is more accurate, etc. So that's how you set K. You do this multiple times, and then you come up with the best K. Is everything clear so far? Yes, exactly. That's a great question. So what is overfitting? Overfitting is when your model is doing an amazing job on your training data, but it's doing a very bad job on your validation and test data. That's when your model overfits. Probably if I set K to be a huge number, I don't want to break the computer, but let's see if it does it. Now we are starting to overfit. So this number being huge is going to cause trouble. Does that answer your question, Keith? Yes, no? Okay. So yes, there is confusion about the concept of overfitting. It's a very important concept in machine learning. Why? Because your final aim is for your model to be accurate on new data that it has never seen before. Overfitting is as if you're memorizing a topic. You're memorizing your training data. And if your model is too powerful, like when K was 100, our model starts to get too powerful, then you're gonna start, your model is gonna start to memorize your training data. It's gonna do a very good job on the training data. It's not gonna do any mistakes on the training data. But then when it comes to test data, it's not gonna be able to give you correct answers. It's not gonna be as accurate as you want. That's the concept of overfitting. So there is always this danger that if you make your model too powerful, it's not going to be able to generalize to new observations. So that's the concept of overfitting. Let me see if I can find a good, yeah, that's a good plot. So this model, uh, the black curve is making some mistakes. For instance, it's making the red and blue to be classified as the same thing. But then actually the black curve is a much better model compared to the green one, because the green one is memorizing your training data. If a new observation comes in, we know that it's probably going to fall here or it's going to fall here. And then your model is going to classify it correctly, the black one, but the green one is going to make a mistake because it's too powerful. This model is just memorizing the data, just memorizing the training data. Does that answer your question? Okay, perfect. Actually, let's do an experiment here. Let's see how it does on training. I need to change this to train and then do our prediction and then take a look at our confusion matrix. Remember this number, it's 57. It's on your test data. Now let's see what happens on the training data. So your model is memorizing your training data and it's doing a better job on the training compared to the test. Okay, our data is very simple. Let's make the data a little bit more complicated with more observations and do the same exercise. And let me change this to 10. Let's change our data to diamonds data. We have been working with this data set for a while now. You have a diamond, you make some measurements on the diamond, and let's say your problem is, if I give you the table size, if I give you the height, if I give you the depth, can you tell me how good of a cut we had on the diamond? So that's our problem. Let's first start with the diamonds data. So this is our diamonds data. We know that we have caret, we have cut, color, clarity, depth. Most of these variables are continuous. Cut is categorical. And we know that there is a log relationship between the price and the caret. So it's better to take a log of the price and the log of the caret. These observations we made earlier. So let's try to do that. And then I'm gonna create, we learned about mutate. Now we're gonna use it. We're gonna create a new variable, log price. It's the log of the price, log caret. And then we are gonna select all of the columns except for color, clarity, price, and caret. Why price and caret? Why are we removing them? Because we already have them. We have the log of them. And then we can take a look at the head of the diamonds and take a look at the number of observations. Okay, that's our new data set. We want to do a classification on the cut variable, and then our dependent variables are our independent variables are depth, table, x, y, z, and log prices and log caret. How many observations do we have? It's a much bigger data set compared to what we just used. So it's much bigger and you have more variable. Let's take a look at the summary. Now you're going to see the importance of normalization. The mean of the depth is around 61. The mean of x is around 5. So it's a huge discrepancy. between the values. Similarly, for x, the minimum and the maximum are from 0 to 10. This is from 43 to 95. So there is a huge discrepancy in terms of the values. We took the log of the price. If we haven't, then we would have problem, because if you do the exponential of these values, the discrepancy is even bigger. So normalization matters, and we are going to follow the standard procedure. We first divide the data into training, validation, and testing. 70% training, 30% testing. Then we compute the mean and the standard deviation. It's the same as before, but on a new data set. We look at the head of our data. Now the values are nicer. They look nicer. This is the number of training data that you have. The mean is 0. We made it 0. The mean per each column is 0 because we just normalized our data. And they have nicer values. It's a nicer range. And some of these values are just outliers. We don't want to remove them. Let's just keep them in this. But some of these big values that you see on the maximum is just outliers. But we are going to keep working with them. Let's take a look at the test. The values are nice, but we know that we didn't cheat when we look at the mean. It's not 0. It's close to 0, but it's not 0, so we are not cheating. We are not transferring any information from our test data to the training data. Now let's do our k-nearest neighbor. This time, we are selecting all of the columns from our training data except for the first one. So we are selecting depth, table, x, y, z, and log price and log caret. Same thing for our test data, and then we do our classification. These are our classes, and how many classes do we have? If we go up there and take a look at the summary, this is our cut variable. We have 1, 2, 3, 4, 5 classes, and the data is not balanced. There are some techniques to take that into account, but for now, we are gonna apply our k-nearest neighbor algorithm to classify cuts based on depth table and the rest of the variable. This time it's gonna take more time. Why? Because you have more observations. So the problem with k-nearest neighbor is its cost when it comes to prediction. So what we are doing now is just prediction. But to do prediction, you need to look at each data and find its 10 nearest neighbors. And that's a costly algorithm. So the bigger your data set, the more time this algorithm is going to take. Now we have our predictions. Let's do our confusion matrix. And now you see that your algorithm is more confused because the data is more complex. It's making 37 mistakes when it comes to classifying fair versus good. Fair versus very good, it's making 2 errors. And fair versus ideal, it's making 1 error. And good versus fair, it's making the most errors. Actually, this is the most errors that it's making. So your algorithm is very confused between premium and very good. Okay, but now we are looking for a single number, and our algorithm is 71.6% accurate. Any questions so far? So one thing that is interesting about k-nearest neighbor is that it doesn't have any parameters. It has a hyperparameter. So there is a difference between a parameter and a hyperparameter. Our algorithm doesn't have any parameters, so no parameters. It has one hyperparameter. Okay, the role of training is to come up with the best parameters. So if you have parameters, then you have to do training. If you have hyperparameters, then you look at your validation data. So next session, we are gonna go into multinomial logistic regression. And it's very similar to what we learned for linear regression, but there are some catches. For instance, the output of this model is gonna be a value from negative infinity to infinity. But our classes are gonna be a value between 1, 2, and 3. And perhaps a better algorithm is the one that's outputting the probability of each class. The probability of this observation being a setosa, the probability of this other observation being a versicolor, etc. And that one we are going to go over next session.